Likewise, over the various climatic cycles that we think the plains have been subjected to, most likely the rocks have worked their way through the soil to the top. So we had a multi-year effort that involved numerous institutions, the Jet Propulsion Laboratory, the University of Arizona, University of Colorado, Washington University in St. Louis, and the Applied Physics Lab of the Johns Hopkins University. And we've used all the assets that Doug and his program could provide to us. We used data from Odyssey, from the Mars Global Surveyor, which is now finished its mission, from Mars Reconnaissance Orbiter, and from the European Mars Express instruments. It's an ESA orbiter that's been operating on Mars for a few years. We think we found a place that's scientifically interesting and also has a good probability of landing successfully. That is, it's relatively safe. So let's begin with the first slide step, and we begin with a geomorphic map. What do geologists do? What we try to do is understand the regional context, the lay of the land. So what we're looking at is called a shaded relief map, and it's almost like an aerial photo, but the scale is very much different. So that blue area is a valley. That valley is only about 700 feet deep, but it's 40 miles from north to south. So it doesn't give you as an exaggerated sense of relief from this image as on the surface. If you were sitting in that valley, you wouldn't see the edges, you wouldn't see the walls. So this just kind of gives you an exaggerated sense of the relief. The brown areas are the uplands. They're the older terrains that have lots of rocks. The blue terrains in the middle, those are blue colors to represent a particular geomorphic type. They represent fill, a very fine-grained material in the valley. We also have a crater, and that's shown in the kind of middle to the right of the scene. That's about 6 miles across. We've informally named it Heimdall. And it's impacted, we think, into fine-grained material. And that fine-grained material has impacted the surrounding areas as ejecta, but it began fine, and it removed the rest of the rocks. So we're landing in a place that will have a very low probability of encountering a rock, either landing on a rock or hitting a rock when we deploy the solar panels. And slopes are all less than about 5 degrees. So those are concerns that we can put to bed to the extent that you can put anything to bed on Mars. Is it interesting scientifically? Yes. If you take Peter's map of water, we can take it down to finer scales with other information. And we expect maybe 5 to 10 inches of soil max over hard icy soil. So we'll get the soil, and we'll get down to the ice table and begin to dig into the ice with our tool, a little rasp about the size of your thumb, to get hard icy material. So that's the geomorphology. You also see a landing ellipse, and elongate kind of northwest-southeast, it's about 60 miles. And it's nested, so it's most likely will land in the small ellipse. It's very high probability it will land within that outer ellipse, but most likely toward the middle. So how do we get to that particular spot? Let's go to the next slide in terms of sighting that ellipse. Those colors took like 3 years to put together. Those are from HiRISE images, an exquisite instrument, an imaging experiment on the Mars Reconnaissance Orbiter. And each of those rectangles is about 4 miles east to west. And in those rectangles, they began as images. And in the images, you can see rocks as small as about 1.5 yards across. And you can actually see the shadows cast by the rocks, so you can get their heights. That map, the color green, means that if you were standing there, and you were standing on an area of about the size of a football field, you'd be lucky to see 2 or 3 rocks bigger than 1.5 yards across. So we've chosen a place that has very, very few rocks. The slopes are innocuous, very low. So from the point of view of relatively safe areas, this is very safe in a relative sense for Mars, among the smoothest rock-free areas on the planet. But scientifically interesting? Yes. If we go to the next slide. This is a view where we're not going. This is off the ellipse to the northwest in a terrain that hasn't been affected by emplacement of this very fine impact ejecta from our 6-mile across crater. These are the old plains, and we actually have plopped down onto the surface a cartoon of Phoenix. Phoenix with the solar panels deployed is about 18 feet across east to west. And you can see that there are rocks with the shadows roughly the size of the vehicle, so it's not a good place to land. That's, just to be clear, to the northwest of our ellipse. But let's go to the next slide. This is in the sweet spot, the most likely location where we'll land. Although remember, there's a probability distribution that goes out to the edge of the ellipse. Very few rocks. I can see from here maybe one or two, but I can see lots of polygons. And these polygons are interesting. You know, they're roughly at the scale of the lander, and our robotic arm can extend out 6 feet relative to the horizontal. So we're likely to land in a place where we can dig within a polygon and also within a trough. And we're interested in excavating and doing a cross-section to see the ice table at both, and to sample soil and ice at both locations to be able to test hypotheses relative to current and past climate and habitability. So that's how we got to this landing site and some more of the science. And let me turn it over to Barry Goldstein, the project manager. He's going to tell you how we're going to get there.
Okay. Thanks, Ray. First, I want to start with just an observation. Since I work in Pasadena, I probably have to make reference to the fact that Grandma must be the little old lady from Pasadena, because Grandma's car is pretty well understood and is pretty high-performance vehicle. The teams at Lockheed Martin in Denver and JPL have been working for the last 5 years to really understand how this vehicle works. And as many as you know, since we inherited a lot of hardware, we spent a lot of effort in testing this vehicle and understanding how it works. I'll talk a little bit about getting to where Ray talked about. Can I have the first image first? We launched Phoenix on August 4th of last year, and currently we are about 410 million miles in travel distance since launch, and about 12 million more miles to go till we reach the planet. Relative to Earth right now, we're at about 170 million miles away, which takes light about 15 minutes to arrive, for reference. The team has been working on this. The team at Lockheed in Denver have been working on this for quite some time, along with the JPL navigators. And we had actually planned to do 6 maneuvers to target the landing site that Ray discussed. At this point, we've actually executed 3 of those maneuvers. However, the vehicle has been operating so well that we had planned a maneuver this past Saturday, and that's been postponed and waved off because we don't need it. Our next planned maneuver is this coming Saturday, where we'll fine-tune the objective or fine-tune the trajectory to land at the center of the ellipse that Ray showed. And then we have another maneuver, if necessary, which we'll execute 21 hours before entry. Now let me talk about the main event, the 7 minutes of terror, as it's been called. Can I roll the next video? Okay, approximately 14 minutes before touchdown, 7 minutes before entry, the vehicle separates from its cruise stage. At this point, we lose X-band or direct communication, and all of our communication through the vehicle is now coming through the relay orbiters of Odyssey and the Mars Reconnaissance Orbiter. In real time, we'll be receiving data from Odyssey and Doppler only at this point, or engineering data only at this point. We enter the Mars atmosphere in 7 minutes, and we're now traveling at 12,600 miles per hour relative to the surface of Mars. We spend 4 minutes going through the atmosphere, taking out 94% of the energy. By the time the heat shield has done its job, we're down to 1,100 miles per hour. At which point, we fire a mortar, and if the video shows it soon, here you'll see the parachute deploy. 16,000 pounds of force is what we tested that parachute to at peak force. It rides on the parachute for approximately 3 minutes, depending on various conditions, atmospheric densities and other conditions. And about 10 seconds after we deploy the parachute is when the heat shield deploys, and hopefully we'll see that on the video here really soon. And there the heat shield is deployed, and the landing legs will deployed. Once exposed, we then activate our landing radar, and we can get the actual height to the ground. We separate from the back shell and then turn towards the planet and start firing our propulsive descent engines. As Ed mentioned, this is the first time since Viking that we use thrusted descent, but unlike Viking, we have pulsed engines, which is different from Viking. We've characterized those as well. Just before touchdown, we actually pirouette the vehicle. We actually turn it so that we maximize the solar exposure. After touchdown, we wait approximately 15 minutes before the solar rays are deployed. We're waiting for the dust that we will